Coulomb branch. Please, Viktor.
Thank you. Okay, so first of all, I'd like to thank the organizers of the conference for organizing the conference and for inviting me and giving me the opportunity to speak here. So, yeah, I'll talk about this work that we put up on archive, I think, a couple of weeks ago, maybe even earlier, with all these people. So, as evident from the title, it's concerned about n equals 4 super Young-Mills theory on the Coulomb branch. Mainly, we will focus on, technically, on computing one-point functions and two-point functions and studying various properties of their properties and some related questions. So let me start by hopping over some of these questions and the motivations for this work. So one reason to study the Coulomb branch is because in that case, obviously, one-point functions of operators are non-trivial, and in general, expectation values of operators are important quantities. So it's well known that in the studies of non-perturbative physics, one-point functions or vacuum condensates play an important role, such as in the QCD sum rules or in resurgence phenomenon. And in general, they are quite complicated to study. So, of course, it makes sense to do this in the controlled scenarios where the vacuum structure is known and where renormalization of operators is well controlled. So this is kind of a very general motivation. Then a slightly more specific one is to study spontaneous breaking of conformal symmetry. So one may ask a general question, if we have a conformal symmetry, does it allow for a vacuum manifold or any kind of conformal symmetry breaking pattern? And the nice kind of, again, the nice point to study it is the n equals 4 theory. So what kind of questions we can ask here? For example, we can ask about the convergence of the OPE expansion in this vacuum state. So, and if we kind of deduce that the OPE is convergent and well-defined, then we can compare the two-point function of some operators to the expansion of this two-point function in one-point functions according to the OPE. So if these are some OI and OJ, then this CIJK, okay. And so, I mean, this equality itself will impose some constraints on the OPE coefficients so that they are consistent with these expectation values. Moreover, we can do large distance expansion of this two-point function. So this is the short distance expansion. We can do the large distance expansion, and we expect that from general properties that the leading term is just the factorized product of one-point functions, and then we can also add the deduce subleading terms. And again, on general grounds, we can suppose that the leading contribution is given by the exchange of the Goldstone bosons due to this broken conformal symmetry, so which have a behavior as 1 over x squared. And I will later discuss this term in the n equals 4 setting. And so by equating these two expansions, if we kind of know that they are well-defined and convergent, we can impose constraints on the OPE data such that, I mean, if the constraints are satisfied, they do support a Coulomb branch point. If it's not satisfied, then they don't. So yeah, so this is a kind of thing that we're going to study in this setting. So then next, there are two more questions which are kind of specific to the n equals 4 setup, or more specific to the n equals 4 setup. These are the questions about the deformation of the known properties of n equals 4 theory to the symmetry breaking points on the Coulomb branch. So specifically, this provides, or could provide us, will provide us with an example of non-conformal holography. So we'll study the holographic setup that's dual to a certain point on the Coulomb branch, and it will break conformal symmetry, so it's a simplest example of non-conformal holography. And also, again, non-conformal, or in general, different backgrounds of and the deformation of integrability. So, yeah, so we're not gonna go too far into exploring integrability. However, we're gonna set up a few calculations that will show that the special point on the Coulomb branch that we want to study is perhaps integrable at any coupling. So, so on these points there have been various works. So specifically, what we do can be compared to the defect CFT setup, which is dual to this D3, D5 brain configurations, which were studied by the NBI group, basically, Charlotte Christensen and co-authors. And so one can show, one can basically answer both of these questions in this DCFT setup, show a holographic, dual holographic configuration, and also study integrability, and show that integrability can be extended for these one-point functions. Integrability can be extended to generic coupling. So the plan of my talk is to describe several calculations that we did. So basically, there are three things that I'm going to do. I'm going to compute one-point functions at weak coupling. So to one loop corrections. I'm going to describe the holographic setup. And I'm going to compute the two-point functions. And then study the IR and UV expansions. So what I don't mention here is that also in our work we consider the question of, I guess this should be another point here, of large charges. So unfortunately, I realized I will not have time to talk about this. So this concerns the relation between large charge operators and the Coulomb branch. So as we also heard in the previous talk, kind of large operators can can impose some holographic dual solutions, such as dual gravitons, and also can put the theory on an non-trivial background. And yeah, so in this at the special point that I will now describe, we also studied the correspondence with large charge operators, but yeah, I'll not talk about this today. So let's start by just describing what kind of vacuum are we talking about. So in n equals 4 theory, we have, among other fields, a set of scalar fields, which I'll call phi I, with I running from 1 to 6. And the potential for these scalar fields is this trace phi I, phi j squared. So if we are concerned about coordinate-independent solutions, then we should just minimize this potential. It can be minimized by any set of mutually commuting matrices. And the point that we choose, so the classical solution, is the following matrix. It's Vi in the upper leftmost corner, and then 0 everywhere else. And so we will denote the kind of norm of this vector as v squared. And also sometimes, for simplicity, if we want to kind of forget about the R-symmetry structure, we can just take this vi to be pointed in just any specific direction. So this vacuum breaks some of the symmetries. So first of all, it hexes the UN gauge symmetry to U1 times UN minus 1. Then, of course, it breaks conformal symmetry to its Poincare subgroup, and it also breaks the R symmetry spontaneously. So to compute any kind of loop corrections to tree-level quantities, we will expand our fields around this classical solution. So the fluctuation fields will be called phi tilde. And so looking at the Lagrangian for these expanded fields, we can classify kind of the field content according to the symmetry breaking pattern. So we'll have a set of fields with indices kk, or this phi tilde kk with k not equal to 1. These will be massless. And of course, the same concerns the gauge fields. So these are massless because they don't feel the vacuum configuration here because of all these zeros. Then we'll have the fields phi 1k with k not equal to 1. These will be the massive fields. So that correspond to the hexing of this gauge symmetry. And then we'll also have the phi 1 field, which is again massless. And this is the dilaton, or rather the Goldstone boson of the broken symmetries. So also because of these kind of separation of indices, we'll have a slightly different large n counting, which will affect some of the computations later. So yeah, and another point to mention, so there are some details about the Lagrangian for this expanded field, so one has to fix the gauge in a proper way, do something very carefully, but I guess the kind of important point is that the important technical detail here is that the propagator for all of these fields can be chosen in such a way that it's diagonal in these ij indices. So which is, for example, in comparison, so it's diagonal. It can be chosen such a way that it's diagonal exactly in the kind of initial basis of these phi tilde fields. So now, as I've described the gauge theory setup, let's compute one-point functions of operators. So of course there are kind of two kinds of operators that we can be concerned about, the protected ones and non-protected. So we'll consider the chiral primary operators, which are the single trace scalar operators. So there'll be some proportionality constant that I'll drop for now. And then they're given by this contractions y phi to the L. Basically, as in the previous talk, this y is a null vector. And then we'll also consider non-protected operators. So, for example, we'll look at the simplest one, the Konishi operator. So there'll be also a proportionality constant. This is given by phi a phi. So these normalizations are could be chosen in such a way that the two-point function is properly normalized. However, For the Kanishi operator, of course, this normalization constant is also important because it's, because it cancels divergences, right? So at tree level, there's nothing really surprising. So we just evaluate these at the vacuum point. So again, this would be proportional to some constant times trace y times v to the L. And then the Kanishi operator, so this is the expectation value at this vacuum. And then for the Kanishi operator, we will have basically v squared. And then here I want to spell out the constant as well to later compare this to one loop results. So this will be normalized in the following way. So before we compute loop corrections to these, there are, I think, two things to mention. So one is kind of the general structure of the loop of the one-point function that we expect. So if we have an operator, an expectation value of an operator in this vacuum V, then we expect it to be at least kind of qualitatively of the form some constant c, depending on the operator, times v to the delta O, where delta is the dimension, like with the proper loop corrections, and c is some constant, which is kind of the dynamical information about this vacuum. And of course, if the R symmetry structure is more complicated, then it will enter this formula as well. So this is kind of just schematic. And the second point is that you want to compute one-point functions in such a way that so we want to extract the finite part of one-point functions. This is what we're interested in. And therefore, you want to make sure that what we extract is scheme independent, so that we could compare it, to say or set up for integrability. So one way to do it, to carefully take into account all kind of renormalization and scheme independence, is to define the one-point functions in the following way. So we take the bare operator without the without any renormalization, compute its one-point function, and then divide this by the two-point function. So we take the square and then next to the delta. Kanishi in this case, so this is just, for example, for the Kanishi operator, but this works for any. So, and then this denominator can be computed at the conformal point. So, and then we, of course, take the bare operators here as well. And this expression, well, of course, so this is x coordinate independent, just because of this, because of conformal symmetry. But this expression is manifestly finite and scheme independent, at least for multiplicative renormalization. Because if we renormalize this bare operator by any kind of z factor, then it cancels in the denominator and the numerator, and also any kind of finite scheme change also cancels here. So this expression is manifestly scheme independent and finite. Right, so as I said that, we can now compute the loop corrections. So what kind of loop corrections are there? So let's introduce some notations. So, if we just consider some operator with a few scalar fields sticking out of it, then the tree level contribution we will denote by just this, like putting all the scalar fields to their vacuum value. So then the loop corrections are of two types. So one is when we put kind of most of the fields to their vacuum value, but we can contract two of the internal scalar fields. And the other one is when the loop runs on one external leg, meaning that, so this is kind of the renormalization of the expectation value of the fundamental fields themselves. So of course here one should be careful about the n counting, and also, so obviously when I draw this, I mean that here we contract the scalar fields with the massive propagator. So this is a contribution of these phi1k fields here, because of course the massless one would just vanish because it's the same computation as at the conformal point. So one can show that these contributions vanish. Basically, they vanish due to supersymmetry. So this it means that the expectation value of the fields themselves are not, these are not renormalized. So, but these are non-trivial. And again, there are two cases. So for chiral primary operators, in fact, this diagram also vanishes. So these are not, they don't have loop corrections, so they are tree level, actually. And this is due to the fact, as I told earlier, that the propagator of these fluctuation fields is diagonal in the ij indices, and this is just the tracelessness or the null vector condition, the null vector condition for these chiral primary operators. And then for non-protected operators, we of course get loop corrections. And just to give one example, the simplest one, for the Kanishi operator, which we compute with this prescription, we get the following result. So here I want to just spell out all the constants in this one example. 3 lambda over 5 pi squared, gamma plus logarithm of v over 2. And so we see here the anomalous dimension of the Kanishi operator. So this can be actually reorganized according to this structure that's dictated by conformal symmetry. So we can write this as 4 pi squared over square root 3 lambda plus square root 3 gamma minus logarithm of 2 v to the delta k, where of course here I assume that I write the one loop anomalous dimension of the Kanishi operator. So this can be actually compared to this D3, D5 setup. So in particular, the kind of main difference, for example, is the tree level exactness of chiral primary operators. So in the defact CFT setup, chiral primary operators, their one-point functions also get loop corrections, even though the operators themselves are not renormalized. And also an interesting kind of observation is the appearance of this Euler gamma here, which is, well, in loop computations, this Euler gamma is usually kind of scheme dependent, but here the expression is manifestly scheme independent, and it still appears. And this also is present in the D3, D5 setup, and is related, or is related to integrability. So mainly this Euler gamma kind of is important to match integrability calculations. So this kind of hints that maybe this also might work. Another hint is that, so if we consider generic operators, scalar and single trace, so suppose we have an operator with some wave function psi I1, psi IL, trace of phi I1, phi IL. So then we can compute the expectation value of this operator in our vacuum state. And at tree level, at tree level, it turns out to be proportional. It can be expressed as some, of course, proportionality constant, and then the overlap of this wave function with a specific boundary state. And this boundary state is very simple, is given just by kind of the product of unit vectors, a L-fold tensor product of unit vectors in the direction of our vacuum state. And in fact, this boundary state was already considered by Christensen and co-authors, and it was shown to be annihilated by infinitely many charges, and so like therefore it can be called an integrable boundary state, and these overlaps were actually computed as well. So this means, so this kind of shows that this setup is also in this sense, integrable. Moreover, if we compute one loop corrections to this to generic operators, then we find a very simple expression as well. So the one, or yeah, so I can write it as a 0 order, like plus the first order. So it's the tree level plus the one loop contribution. It's also actually expressed via this overlap. And then the correction to this expression is very simple, and is just expressed via this anomalous dimension of this operator. And we have this factor log v over 2 plus gamma, which again can be exponentiated in this form. And this kind of simple form of the loop correction is due to the fact that the one loop correction to this boundary state that appears here in the computation is actually proportional to the action of the mixing matrix on the, so the one loop correction is proportional to the mixing action of the mixing matrix on the initial boundary state. Yeah, so, and well, in the paper we considered a bunch of examples for, I think, up to level, up to length 4 operators, or length 5. But then, so this basically sets up the problem to be possible to analyze from the integrability perspective. So there are a bunch of hints that kind of make it seem like it's possible to extend this analysis to finite coupling. And we have a ton of initial data, well, kind of to compare the calculations. So let me now go on to describe the holographic setup. I actually don't want to spend too much time on it because the calculation is very similar to the standard, or actually is basically the standard holographic prescription with a very slight modification. So we will compute the one-point functions. Of course, now we're only talking about the protected sector. And so we will compute the one-point functions of some. Yeah, so we can write these as C, I guess, because we're talking about the chiral primaries. So we are going to compute them according to the standard prescription. So we'll take some supergravity action, some gravity action, and then vary it with respect to boundary condition, where we just need to identify the modes that are dual to these chiral primary operators, but this has been, of course, done long ago in the literature. So the only modification is that we now need to modify the gravity action in some way, because, well, otherwise we'll just get 0 as usual. And so basically the holographic prescription here can be kind of pictorially drawn as follows. So we have the standard brain stack, D3 brains, that form our ADS5 cross S5 background. So, however, what we do now is we take a single brain and detach it from here. So this is a single D3 brain, and it's placed parallel to the initial now n-1 brains, but this, of course, does not, I mean, so this brain does not change the ADS5 cross S5 background, but acts as a probe, similarly to the D3, D5 setup. And what we need to do now is only to match the distance at which it's located to the vacuum expectation value. And this can be done either by just doing the calculation and matching two formulas, or by comparing the energy of a string that's that is between the initial stack of brains and the probe one, and comparing the energy to the mass of these massive particles, or either to the scalars or to the gauge field, so to the W bosons. So in any way, we get that the distance at which the brain should be placed is given by square root of lambda 2 pi v. And then to describe the interaction of the supergravity modes with this D3 brain that's placed in the bulk of ADS, we just modify the gravitational action. So we have the standard kind of supergravity action, which does not, of course, contribute to the one-point function, but we modify it by adding a dBi action for this D3 brain. And after that, the calculation is pretty much standard. And what we get is an exact agreement between the tree-level computation here with the proper proportionality constant and the supergravity, the strong coupling calculation here. So this kind of is in good correspondence with the fact that the loop corrections to one-point functions were vanishing, meaning that it basically proves that the one-point functions are tree-level exact, well, because they are equal at tree level and at strong coupling. And this is again in contrast with the D3, D5 setup, where the operators receive loop corrections at weak coupling, and this has to be compared with the strong coupling result. So in the last 10 minutes, right, I want to compute and discuss the two-point functions. So I guess I can leave some of this here. So I want to discuss the properties of two-point functions, mainly using one simple example. So let's take the simplest chiral primary operator trace z squared, which we will for now not normalize, where z is of course phi1 plus I phi2. And as I said, for simplicity, let's choose vi to be delta I1 times v. And so we can compute the two-point function of this operator. So there are several diagrams that can contribute to this. So let's draw the operators like this. So then, of course, the leading order correction is just putting all the fields to their vacuum expectation values, which will give us a v to the 4 here. And this is basically the contribution, the disconnected contribution of two one-point functions. And then there are a few other diagrams. So one is, now I have to draw this in double line notation to be more precise. So one is we simply have the contribution of these phi kk fields, which are massless. So this gives us the same result as we would expect at the conformal point. So the fact that there are n-1 of these fields does not affect anything at large n. So we get lambda squared over 8 pi 4 to the x to the 4. But then the interesting contribution comes actually from the massive field. And so we can also do the following. So here we put the vacuum expectation value, but this actually enforces these lines to have index 1. So these lines here have index 1, meaning that I will draw this with a dashed line, meaning that this line here should be the massless phi 1 1 field. And since I mean, we have less fields. Since we specified the index, we lose one order in 1 over n, but then the result, this kind of simple tree-level exchange gives us the following. So, and this is actually the 1 over x contribution of the Goldstone bosons of the broken conformal and R symmetry. And finally, we can also take, again, two propagators, but then make one of these lines here dashed, meaning that its index is also 1. And this makes these lines massive, and this gives us, I think, so it's, again, something proportional to the square of a massive propagator. So there are two regimes that we want to look at. One is the long-distance expansion, one is the short-distance expansion. So at the long-distance expansion, we see that this dilaton exchange term is actually very important because it gives us the leading, well, of course, the leading one is the disconnected, but apart from that, the leading contribution is this dilaton exchange. And so, well, in the IR, well, I don't really want to rewrite this because, yeah, basically everything stays the same, except for we take the IR limit of the massive propagator, which gives us an exponentially decaying contribution of, yeah, of this kind. I think x to the 3. But yeah, so the point is that the dilaton exchange here defines the leading IR contribution. So the interesting kind of part, even though it's 1 over n suppressed, this is kind of the interesting part. And then the UV expansion gives us, so if we now normalize this slightly, let me just spell this out completely. So this is the UV expansion, and this can be compared to the OPE expansion of our operators. And then here we clearly can identify the contribution of the identity operator. And then we have two more contributions. One is from another chiral primary operator, O tilde, and this gives us this x squared. And then there is also the Kanishi operator. And this, so this actually gives us this contribution. So as we can see, this UV expansion has these logs, and these logs, well, should be responsible for some kind of anomalous dimension. But I mean, obviously, these two operators are protected, so they actually, well, they shouldn't have any anomalous dimension. So this actually comes exactly from the Kanishi operator that appears here in the expansion. And this is also kind of a nice thing to look at, because I mean, so, like, we take two protected quantities, but we see that inside we have some kind of loop corrections, and we see that we should identify them with loop corrections to one-point functions of non-protected quantities, and this actually kind of imposes a set of constraints or rather relations between various loop contributions. So the one loop contribution to two-point functions and one-point functions of the Kanishi, which are computed at the conformal breaking point, are in interplay with the one loop corrections to the OPE coefficients, which are computed at the conformal point. So there are some kind of very nice, seemingly relations between these various contributions. So I want to end with just one last formula. Which concerns the dilaton term. So one can actually fix this, the proportionality constant that appears here. So if we look at generic operators, O1, O2, and then we only consider this particular term, the leading IR, apart from the disconnected one. We call it the disk contribution. One can actually show that this is fixed by a word identity that comes from the broken conformal and R symmetry. So, and the form is given by this formula. So here we have the x squared, and then there's a constant here, phi b squared, which is the form factor of the dilaton, given by this matrix element. So requiring a word identity fixes this structure completely. And what we can check is we can basically compute a, so these are the R symmetry generators here, and we can compute one loop corrections. So at tree level, it's simple to just see the structure, but we can compute one loop corrections and see that this actually holds. And moreover, this structure, this form factor of the dilaton is not renormalized at one loop, of course, which is kind of expected because it should be like a property of the vacuum, but still, we check the structure at one loop and see that it still holds. So, yeah, I guess I'm done. Just want to make kind of recap a few comments, and also, yeah. So we have computed the one-point functions. We have shown that they are their form is amenable to an integrability consideration. For the two-point functions, we have shown that their IR or their IR expansion is consistent with the dilaton word identity. And another fact that I didn't mention yet here is the UV expansion and the convergence of the OPE. So here we can just explicitly check at one loop if the vacuum that we have is, if the OPE is still convergent in this vacuum, even with loop corrections. And so what we see is that if we organize all the log contributions that appear here, that in anomalous dimensions, as in this formula, then the OPE seems to be convergent with infinite radius. And so this can later be exploited to impose various constraints on structure constants and conformal dimensions. And this is actually consistent. So the fact that the OPE is convergent at one loop is consistent with the calculations that have just recently appeared by Rastelli, Coulomb, and Sharon that have also done this in 3 dimensions in other theory, and also shown that the OPE is still a convergent, infinite radius of convergence even at one loop. Thank you.
Thank you very much. Questions?
I mean, so at one loop, it's only Kanishi which appears in OP, or you just ignored higher terms?
Yeah, I mean, well, I ignored the higher terms, and yeah, I mean, this is
so
for
there are only three terms. When you refer to finite radius, infinite radius, is because there are 3 terms on there.
No. I mean, we can further expand this massive propagator, and this will, give rise to other terms here with other dimensions. I mean, of course, we cannot check, I guess, this explicitly, but we kind of anticipate that these logs are always in
just at one loop you may just miss some operators which are being exchanged, and then you have impressions that it's infinite radius. Well, I don't know how can you whether you can conclusively decide
we also compute this. I think we also compute this. I guess we check the OPE for like generic chiral primaries and the Kanishi, but the higher dimensional operators we didn't really explicitly kind of check that all of this organizes into anomalous dimensions and all of that.
I think I missed the integrability statement. So what's exactly the integrability statement? Is this integrable? And can I see it at strong coupling?
No, the statement is just that we computed what we computed is supposed to be like initial data for or comparison, some data that could be compared to integrability, but just from the form of the expressions and that they are similar to the D3, D5 setup, we assume that probably they also can be integrable at strong coupling, but this is not what we didn't check it or kind of. Yeah, the fact that, well, I mean, it's so like at tree level, it's given by an overlap with integrable state. Then we have this, Euler gamma factor that appears, and then also the one loop correction is also very simple and also expressed via this overlap. So it's just like a hint, and then.
But there are no hints on higher loop integrability so far.
Yeah, so far not. I mean, I guess we can compute more loops and then see, or just try the integrability analysis and see if it matches with the one loop calculation.
Also, do you know by chance the paper of Shaposhnikov and Karananas?
Oh yeah, I should have, sorry, this is my mistake, I should have referenced it here. So basically this dilaton word identity is a modification of the one by Shaposhnikov and Karananas. Thank you for the question. You let me correct my mistake. Yeah, so this word identity is a slight modification of what they have because I think they didn't have broken R symmetry, and yeah. So basically, but I think we did not rederive it explicitly. We assumed this kind of form and then fixed the constant here by the tree level, and then saw that it's still consistent at one loop level.
But they had a much more ambitious program there, which probably is far from the possibility of being fulfilled. Yeah, you need really the whole expansion in OP expansion.
Yeah, right. I mean,
but this formula was there.
We're limited to that. Yeah, but thank you for letting me correct myself.
Thanks.
So can I ask? So have in the from the holographic setup, can you say anything about one-point functions for the non-CPOs? Do you have any statements about that? Or?
Well, we don't. And
you don't, I'm sorry, yeah. You don't. You said.
You were asking if we can say something about non-protected.
Yeah.
I don't think so. Yeah, we didn't really. Yeah, I don't know if something could be said about that.
Maybe you have a question. How is this framework resistant to some perturbation, some small deformation of the Lee-Strasser type, for instance, reducing a bit supersymmetry with beta deformation of the theory? Since you're considering gauge group UN and not SUN.
Not sure about that. Well,
my concern would be that with the UN and not SUN, you will likely lose conformal symmetry from the theory, and you still have some use of conformal symmetry, even though it's spontaneously broken, right? Because you have a defect CFT. So I don't.
Yeah,
I'm negative in this.
Like the sort of the conformal symmetry of this theory is there, but the vacuum is not symmetric. But this still imposes a lot of constraints. So
right. So if you use a gauge group UN and you deform it, I believe you will lose really the full conformal symmetry of the theory, and this computation could probably not repeat it.
Maybe, yes. If you lose, I don't know. Yeah.
Could you do a more involved, find a more involved vacuum, classical vacuum, which is still SUN instead of UN?
So that it would be breaking from UN to SUN? Or
no, you start with a theory in SUN, and then you break at that point. Yeah. Using SUN matrices, right? Your classical phi was not SUN, was UN.
No, right. I mean, well, I think if there are many, ways to make a set of mutually commuting matrices. So I suppose you could break a SUN as well. But
Other questions? So if there are no other questions, let's thank Viktor again.